Okay, I'll bring up our first speaker, Mr. Mike Moore from Harris. He's going to talk to us about neuromorphic computing and the challenges and the opportunities out there.
Good afternoon, everybody. Let's see, I'm an industry person, not an academician, so maybe my speech will be a little bit different. But I've had a long career, and I've done a lot of work in computer science and a little bit of chip development. My career includes things like embedded system development, compiler development, some other things dangling in there. Actually did a little medical work for Johnson & Johnson as well. But today's the topic is neuromorphic computing. I think it's going to be an introduction to all of you, so I'm not going into any of the algorithmic details. I'm just showing you the leaves and edges of this thing and open your eyes to what's going to be going on in the future. And the whole goal of my talk is to show you why there is a future here. We start with a cartoon, but the cartoon was really setting up a story. On the left are fantasy, mythology things. On the right are things which are around today. So, for example, we have science fiction movies, Fritz Lang's Metropolis thing from the 1930s, and Asimov's I, Robot. None of that stuff existed back then, and we've all thought about it. Before that, we had puppets. Pinocchio's been in the culture for a long time. Then we have a fantasy car down there from a TV show. But as soon as you move across, there are equivalents that are starting to show up. You'll recognize Echo. You might recognize some driverless cars, a factory robot. What about these guys on the right? I invite you to go to your web browsers and look at Boston Dynamics and take a look at some of these things. They are impressive. But do you see any for sale? Okay, just a little rehash of since neuromorphic computing is associated with AI, and I'm going to show you why it is. A little background on the fascination we've had as a species with artificial intelligence. Way back we had people that were chemists before we had chemistry. They were the alchemists. They tried to cook things up with not really knowing how anything worked. And their theory was that intelligence was a little man that they could somehow make chemically, called homunculus. Before that, the Greeks, go back to Aristotle, they were very interested in thought and meta-thought as well. And they developed this whole logic and reasoning thing. And if you go back to some of your basic philosophy courses, you'll recognize logic in there immediately, predicate calculus. And then in the 1950s, we get these symbolists and some rule-based guys. You'll notice I've got a couple of languages there you might have seen in old catalogs, Lisp and Prolog. Really delightful languages for manipulating symbols. And with these languages sitting on top of the computers of the day, you could just have a lot of fun with what the philosophers were talking about 2,000 years ago with logic. And the idea of beginning in the 1950s was to try to make artificial intelligence by just writing enough rules. So if you have enough rules, something ought to work. And then later on, we got a little bit more computing power, and the people started being able to harness things like Thomas Bayes' concepts on the probability, belief systems, and also graph theory. And then a little bit later on, and we're talking a couple of years now, later on, we started seeing numeric classifiers as a topic of interest. And these delighted especially the people that were math majors, something to work on that they could get their hands around. Again, it's because computers were available, they were cheap. Eventually, the connectivists figured out that if they just have a lot of what they call neurons, maybe we can get intelligence out of it. And then we finally have this more recent thing called deep learning. I'm sure you've all heard the term deep learning, just a more advanced version of the artificial neuron networks that were being played with in the 1950s. But now there's more understood about how those can be used in thick layers. must be dead. Okay, so who's doing this? Who's doing all this work? Well, way back, we had people working on the philosophy, but they were not the farmers. The farmers were trying to feed people. They weren't dismissed. They were too busy trying to make a living building things that people might buy. It's the people with leisure time, sometimes the smiths, never the farmers, and the curious tinkerers, the tinkerers that we now call engineers and technicians. They were the ones that played with what there was at the time, and it's why you've got things like alchemists fooling around. And then we eventually got people starting in the 1950s that thought maybe we can actually build some of these things, and if we can build some of them, then we can play with them with our hands and try to make assemblies. This is a little timeline that's more notional than mathematically exact, but going back in time, you can take that line to the left back a couple thousand years. All we had for shall we say, computation was our fingers, which I guess was the original digital computer, abacuses, and some analog things. Starting around the 40s, we started getting a somewhat serious ability to program things digitally with ENIAC. But there's really only one ENIAC, and it's like a team of people to manage it. And of course, nobody really could buy these things. They were more a curiosity paid for by the government trying to fight a war. And then in the 50s, something special happened. People weren't playing with gears and volts and amps anymore, but somebody thought, hey, you know what? We know a little bit now about neurons, just a little tiny bit, and maybe we can characterize them mathematically. So that was the perceptron. It was the first case of somebody using something called Hebbian learning. It was a guy named Hebb who invented that and got that term, his name applied to that concept. Now, starting around 57, we started getting some good computers, and we started playing with artificial neural networks, these ANDs that you have down here at the bottom. The thought was, if you just put enough of those together, you can make a robot that would do things, that would be alive somehow, that had some level of intelligence. Well, that was nice. The engineers were playing with that, the mathematicians were playing with that, but nothing came of it. We kind of hit a winter of artificial intelligence by 1980, which is about the same time there was enough cheap computing power. By the way, this curve on the y-axis here is calculations per dollar. So as you can get more calculations per dollars, you start getting these other interests popping in, because now you have more curiosity, and you have more history behind it, a little bit more acceptance. So the neuromorphic computing started right around then, when people started to put assemblies of these perceptrons together into artificial neural networks. And then, with still more computing power, the mathematicians popped up and said, hey, we got these interesting functions, these support vectors, and that's these tractors, and also probability theory, the belief systems from D up Pearl. And those started getting developed up until the current time. And then deep learning popped in right around 2000, 2005. And look at how the computing power was rising. There's a correlation there. Okay. Oh, I should go back one. Yeah, see, how do I go back one? I can't read this. I forgot about the red line on the side here. You notice that the graph is going asymptotic to the y-axis. So something special is going to happen if that slope keeps going. And those of you who know enough math, you'll notice we recognize that as a singularity, a point where there's no definition. That's a mathematical term. This guy named Kurzweil put his name to a singularity he claimed would happen right around 2025 to 2050, in that range. We'll talk about that a little bit. His singularity is it will become economical to match the brain's computing power with about the same space and power constraints. So in the space of a human brain, what that would take, You should have enough computing power at low wattage and cheap enough for a lot of people to tinker with it, that suddenly you have something serious. You have the same computing power as the human brain. What could that mean? We still don't have any robots though, even though we're closing in on this date pretty fast. Kurzweil's idea works like this. Technology improves intelligence, intelligence improves technology. Some of you will recognize that as a positive feedback. It's just going to keep climbing and climbing while there's juice enough in people and the economy to keep this thing going. That's the crucial thing, the economy. Why no iRobots? Okay, we got several $100 million been spent since the 1950s. There's been promises. In fact, if you had the privilege of attending some of these AI get-togethers at places like Carnegie Mellon and MIT, at any of the major good universities that have a lot of money to deal with this, you'll hear people talking about 10 years from now we'll be able to do this, 10 years from now we'll be able to do that. Well, it didn't happen, but we're still hearing it. The question is, why don't we have any robots yet? Why is that 10 years still off? We have the computing power. We can build it, but we don't know what it is we're going to build. Say, it's a brain, right? It's intelligence. We're going to make intelligence, but we don't even know what that means. So how can you build it? Okay, we've got this growth of computing power that you've just seen. Gordon Moore was the one that talked about that back, I believe, in the 70s. He said that things are going to get smaller by 1/2 every 18 months. And sure enough, we've been on that curve. And we're still on that curve. 3 years ago, a group I was with was playing with 64 nanometer technology, but now we're playing with 16. And we're not the leading edge. Leading edge is down around 7 or 8. And I'm sure in a couple of years from now that's going to change. That's pretty darn small. However, there was a corollary that things get twice as fast every 18 months, and that has stopped. Our computing chips now are typically topping out around 33 gigahertz. You're not seeing things much faster unless they're special purpose things. So something is falling out here. How can we keep getting more computing power if a computing core can't go any faster? What's the motivation for trying to make it go faster? Well, what you can do is you can put multiple cores on a chip. In fact, UC Davis has, this is a couple of years old here, has a chip with 1,000 cores on it. Now, they're not cores like general purpose computers, but they are cores. It's only a matter of time, maybe a decade, maybe a little more, until we have something close to 1,000 cores of general purpose computing on a chip. Then when you mass produce that, guess what? You pick these chips up for $100, you got a supercomputer. Just exactly how do you program that? Anybody here ever program a parallel algorithm? How about a system? How about a complicated system? Well, the price goes up really quickly, faster than that curve you saw on one of those graphs. It really rises fast. So it's not likely that we can continue with the same programmable computer technology for those classes of machines that we're going to see coming out pretty soon. Right now it's common to go over to Walmart and buy a 5 to 8 core machine. That's at the retail store. What do you think is in the back room at the big shops? So, do we have an example of something that's extremely parallel, that does a great job? And the answer is the brain. A brain is a parallel computing system, burning less than 45 watts. That's pretty good. Does a lot of computing power, a lot of computation. It does perception, it does cognition, it does motor control. It's very general purpose, more general purpose than any computer's ever been assembled. That's the other part of Kurzweil's singularity. So when we hit the point where we can put together something like a brain, then suddenly there's an inflection point in our total society. And by the way, this thing programs itself, right? That's why we have schools. Still costly, but with one of these brains, if you put together one and train it up to be really, really smart, then you can just copy it. Not unlike our own brains, you can't copy them. So why no brains yet? Well, we have good drones. Again, I take your attention to the Boston robot people. They have great demonstrations online. But all these impressive things that you see really cannot sit down and become inspirational. They don't think like people. They don't have minds. Their minds are more like rule-based, with maybe a dull concept of machine learning involved. So what's going to change? Well, now there's an economic incentive. One of the incentives is on the page here. It's the self-driving cars. There are many, many incentives to push this kind of technology, to harness these parallel cores using some form of machine learning to do general purpose computing like a brain would do. If you can harness that, it becomes amazingly valuable. So automation to intelligence, that's the transition we're trying to make. It's the transition we've been trying to make for 2,000 years. The difference now is that it's driven by industry, driven by profit motive. It's no longer the tinkerers. Now it's the Smiths and the farmers, because now they got skin in the game, and they're going to work like heck as an industry to make this work. That means investment, and that means effort. The trends here are always to reduce labor so they can make things cheaper. Of course, the productivity and equality. Of course, innovation. Where are you going to find innovation? Oh, you got to reverse engineer the brain. If you don't know what the heck a brain is, if you don't know what a mind is, how the heck can you make one, right? Okay, so what does a brain do? Any engineers know that? Okay, now how about mathematicians? Those are the people who have been working on this, right? Up to them now. How about philosophers? They think they know what the brain does, but they don't know what the brain does. So who does? The closest we got are the psychologists and the sociologists, and also the biology people. They've never done this tinkering. Well, if you got to understand what the brain is, you got to know what its architecture is. What are the parts? How are the parts arranged? A brain in a human has 1 billion neurons. Each neuron connects to about 10,000 other neurons. Extremely small spaces in there. How many people think brains are built out of neurons? Anybody? You all think it's a trap, right? For every neuron, there's 10 glial cells. Ever heard of a glial cell? Well, they're there. They're supporting the brain, and they're very involved with keeping those neurons busy and alive, and also, in many cases, affecting what they do. Affects their timing, affects their modulation of signals. So, if we start at the ground level with all these little tiny parts and amazing amounts of connections, how do you make a mind out of that? Well, what's the mind? Okay, this is something I grabbed off the web. This is about 3 or 4 years old. Functional MRI. What you're seeing here in these colors are the larger groups of neural cords throughout somebody's brain. You're not seeing the neurons. You're seeing things that are maybe 1,000 times thicker than the neuron. But it does give you an idea of the networking within the brain. Those are all network branches. It's not the local area networks, those are the long-range networks. If the brain is not digital, what are those neurons doing? Okay, what the heck can they be doing? Well, we know they signal each other, right? You've all heard of synapses and axons and all that. Let's skip over that. Let's suppose neurons make assemblies which do some kind of a function. There's been some things that people have been able to build out of artificial neurons. Nobody can yet take real ones and play with them, right? That's something in the future. But the artificial ones, they've been able to make these deep recursive neural nets that you've heard about and perform deep learning. They've been able to make something called an attractor, and I'll talk about an attractor. Anybody ever heard that term, an attractor? Couple, one person, okay. Let's see, it's kind of a form of memory. And also, I've got down here maybe a belief system. Also, dynamical systems, networks of attractors and other parts. How about dynamical systems? Anybody ever hear of that? Same guy heard of that? These are all topics, by the way, in your college catalog. Polychronic neural nets. That's something that, kind of a way to put these things together so you can use neurons to serve multiple purposes, just by modulating how the timing works. And then something called confabulation networks. That's a speculation by a guy named Heck Nelson. And that's was demonstrated with a system that had to like compose of sentences, kind of sometimes nonsensical, sometimes scary, believable sentences. It would put 2 to 3 sentences together. What it would do is read 500 books, and then you start out a sentence and it would produce a few sentences by putting together concepts it saw in the books and generating sentences which appeared nowhere in those books. So those are speculative mechanisms of cognition, but of course it's speculation. Here's something I grabbed off the net just to show you what a deep learning network is. Each one of those circles represents an artificial neuron, and it propagates left to right. And what you see here is that each layer connects to everything in the next layer. Now, I won't go into details, but what learning happens here is amplifying or inhibiting the connections between these things, going forward and going sideways. It takes a long time to train a deep neural network, but once it's trained, it's pretty darn useful. That's kind of the basis of our speech recognition, our self-driving cars, and many other things. Attractors, okay. First of all, it's a metaphor. It's a metaphor taken from gravity, that attracts something. So I've got a little picture I put together of a plane that's kind of like a net that's got dips and rises in it. And the red marks are where there's divots. So if you took like a ball and rolled it, started it at any point on there, that ball might roll in to one of those things because it's attracted by gravity. So mathematically, if you had like a belief system working on one axis here, where each one of those columns was a different kind of belief that you may have come up with, like, I don't know, red dogs bark a lot, that kind of thing. Then you have observations, but the observations are incomplete. The observations will start you somewhere on that net. Then you'll roll in to a belief basin. That's how those things work. And those have been very successful as well for artificial perception, visual systems. Okay, what do you do to reverse engineer the brain? You got to figure out what the brain is. The architecture affects function. That's something what you don't see in a lot of the industry today. The architecture is just whatever the people who are tinkering with the deep learning networks, the attractors, whatever they put together that day. But in a real brain, there are constraints with the shapes of the networks and the types of neurons that are connected to each other. Seemingly impossible computing speeds come from slow parts. If you took the average propagation speed of a neuron, say in your visual system, it's somewhere around 20 milliseconds. Some people would say 50, some people would say 10. Now consider a major league pitcher. He's 60 feet away from the plate. He flings that thing at 90 miles an hour. The batter has to hit it. To hit it, he's got to detect the ball, plot the path, and then orchestrate arm movement to swing the bat to hit the thing. If you take out your, shall I say, slide rule, or your calculator, and figure out how much time is involved, it's about a half a second from the time it leaves the pitcher to the time it's in the glove. Well, if you take that half second, divided by 20 milliseconds, you got maybe 50 layers of neurons. 50? And we got billions in there. But somehow a forward layering of 50 is your limit given the time. So how does that work? I can't answer it, but it's one of the things that has to be answered. And if you want to go into afterwards talk about that, I can draw pictures of the architecture of the brain and how that might work, but it's only speculation. Okay, what are the tools of the trade to reverse engineer the brain? One of them is neuroscience, limited by its tools. For example, in neuroscience, we would love to disassemble a visual cortex or an auditory cortex. But graduate students have rights, and they just won't let you do that. Behavioral science, that's our psychologist friends and the associated sciences. What they have to come to the table with is they have sets of illusions that they know about, reaction times, different classes and types of behaviors, mental illnesses and mental abilities. And then they can compare that to animals and compare the animal brain anatomy to that of people. Trauma. Trauma is a real important source of information. Anyone here ever hear of Phineas Gage? He's the most famous trauma patient. If you take even an introductory psych course, the first thing you get hit is Phineas Gage. This is about 100 years ago, building the railroad. He was packing some powder into a tube to blow up some rock. Been looking over it when it went off, and it sent a steel rod about this big, about that thick, through the side of his head and up through the top, and just blew out. And then it knocked him over, and he got up with a giant hole in his head, and he walked over to the doctor. And he survived it. And he's a little different. He didn't lose much motor control. And people say his personality changed, but that's an awful lot of gray matter to lose. Why didn't Phineas die? Then we have computational neuroscience. Those are the people with the computers putting together all these models. I've had the privilege of doing that myself. Right? Dr. Bill helped me do that a few years ago. So given the computational skills, say, of you people, you take the concepts from all these other fields and you test them and you say, is this doing what it should do? It's the only way we can learn here. Just a reminder for those who don't know what a neuron is, they're pretty small. And what they do is they have these things coming out called dendrites, which are not yellow in this case, that collect information. And then if they feel like it, they'll send a pulse down the thing that has got yellow on it, and then tickle other dendrites and other neurons. It's more complicated than that, but that's the general idea. So when they put together these perceptrons, the artificial ones, the idea was you have something to take the sum of all the voltages from a lot of wires going in. By the way, not 10,000 of them. Okay, not a bunch. And you take the sum, and somehow they're weighted on the end, and those weights, you change the weights based upon learning. That's called Hebbian learning. Then there's a threshold detector, and if you meet the threshold, it pops out a pulse. And then you can represent that with a pretty simple equation. And then you can go to town making a huge computer program representing neurons. I have neurons. Okay, this is more like a real neuron. This is an electrical model. And guess who does this? It's not the AI people at all. It's the pharmacology people, the pharmacy people, the people making drugs. They're trying to model how neurons really work. A great deal of detail is needed. These models started being produced in the 1960s, I believe. Huxley models are called Hodgkin-Huxley models, and they've progressed pretty darn far. But if you're dealing with these models, the computational overhead is so fantastically high that you really can't use them for AI research. Okay, so there's an example of electrophysiology model that you might find on the net. There's this thing called the Book of Genesis, which is about 15 years old, 20 years old. You can download it, and it will tell you how this stuff works. It's one of the early systems. It's free. If you want to tinker, it's free. How about, well, there's a more modern one. Maybe I left it out. Maybe we'll get to it. Okay, here's a little bit about gross anatomy. Just a little bit to tickle your fancy here. Here's a brain. I colored in the different areas, the frontal, the prefrontal cortex. The temporal is gray. Towards the back is gray. It's the visual cortex. Well, that's what you see mostly is like a layer that's on top of what's called the old brain, you know, the subcortical. Half the neurons are in this medial cortex, and that's what people have that the lower animals don't have. Okay, that's the big difference. Gorillas have them, but they have different ones. The temporal lobes are significantly different. It's the main difference. So, if I can show you that. It's kind of right in here, the difference between gorillas and people, maybe a lot like that. If you were to rip that off and hold it up, it's about the size of a dinner napkin, and it's pretty thin. It's about described as the width of about 3 or 4 poker cards. And in that, you have a bunch of layers. This is from the visual cortex. That's picked because it's a fatter layer, and it's easier to see. These stains that they use are quite old, but still quite effective. And with this, you can see different densities in these neural layers. And those really represent connectivity differences. Intense connectivity where it's fluest. The top layer is like input-output. The bottom layer is input-output. Okay, here's a surprise. Here we're looking down at a brain that I grabbed off the web. Hope nobody not minds. I put arrows on it. You can see the eyeballs. And there's about 800,000 neurons coming from each eyeball. And then you do a little exchange where half goes one way, half goes the other. And you end up with the second red arrows, same amount. And then they get to these things, right here, one on each side, called a lateral geniculate nucleus. Those are interesting little integration areas. Nobody really knows what they do yet. There's some theories. But here's food for thought. The information keeps going towards the back of the brain where your visual center is. By the way, this is where, when you're walking on ice, you should have something patting the back of your head. Every year you'll see in the news somebody falls and they're blind forever. Hit the back of the head on the ice. Common problem. Okay, so it gets to the back of the brain. We've gone through approximately 3 neurons by now, feeding forward. But then there's a rush of neural activity going back to the LGNs. 4 times the bandwidth going forward. What you see is more of what you expect to see, not what you're really seeing. What you are seeing clearly is, hold your hand out, look at the thumbnail. That area is approximately what you can see clearly. How come I can look around the room while your eyes are dancing all the time? Sample, 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 5 times a second, you're sampling. And you're filling in with memory. That's what you're really seeing. Our minds are what our brains do. So we look at different things to see if our brain models are doing what the behavioralists say they do. That's one of our tools, illusions. So I'm going to take a look at just a few things for fun to close this off. Illusions, stories, some expectation things, and then something about behavioral science. Anybody see anything? Is that working? Does it look odd? Stare at one of the black dots and see if the other one moves. Depending on the optics, you might see it. Anybody see that? Nothing's moving there. That's how your perception circuits work on that thing you just saw with the lateral geniculate nucleus hooking to the back and then feeding forward. So if you build a perception module, you really want to represent what a person sees, it's got to have that kind of effect. How about this? See that A and B there? This is an old illusion. It's really terrific. Which one's brighter?
They're the same.
Yeah, they are the same. Most people see B as brighter. I'm just going to move a little something on top of that and see what happens if you experience them being brighter. Now they're the same. That's because contrast in that early part of the visual system is controlling your perception of brightness on little areas. So depending on what's next to it, it affects how it modulates the contrast. Another thing is confusion. Our brains hate confusion. Whenever we are confused about anything, you walk into a room and what do I see? For an instant, you are confused. Okay, this could be the basis of why we like stories, why stories are important. Okay, so I fell back on Pete Seeger here. Some of you may be able to feel this. You've got to get a neurotransmitter rush on this. You might feel it. You might be familiar with where have all the flowers gone? Where did they go? I don't know. Oh, young girls pick them, right? Okay, you might feel that rush. Most people memorize this thing on the first sight. Where did young girls gone? Yeah, got to answer that. I got it. Where the men? They went too. You know, it keeps going, and then at the end it closes. It closes the circle. Then you get a big rush, and you go out and buy the album. You know, the commercial aspect there. But that tells you a lot about how brains work, about how humans think. Bases of storytelling. So we hate confusion. Our eyes only see a little bit of our perceptual field. So if you turn down the lights and you're thinking about ghosts, you're priming your visual system and your memory to fill in ghosts on that feedback circuit that's 4 times the feed forward. Anybody see a skeleton, or do you see a lady putting makeup on? It's an ambiguous thing. Depending on your initial expectation, you're going to modulate one way or the other. Anybody see the woman? Yeah, you all see the skeleton. Okay, remembering attractors, forming conclusions. You can think of an attractor in this situation where the little ping pong ball falls somewhere in the data of your visual field. It falls into an attractor basin. Where it starts out is important. If it starts out for a belief where you're going to see a ghost, it will fall in there. Okay, how do we settle anxiety? There's different strategies. One of them is binary thinking. If we can't handle nuance, then we have to resolve everything to be right or wrong, black or white. And you meet many people this way. Certitude is a practice for avoiding anxiety. If you have contrary evidence, ignore it. That way you won't feel anxiety. If you really want to think about something, you've got to fight that anxiety. And my favorite is the Dunning-Kruger effect. This comes out of Cornell. It's a bias for low-ability individuals suffering from illusionary superiority, mistakenly assessing their brightness. So let's say that the dumber you are, the smarter you think you are. I don't know, anybody ever meet anybody like that? Okay, so how can we succeed in pushing forward here? And the way we succeed is we use everybody. I just assembled a few topics here in the graphic, the cognitive people, the dynamic system people. And I listed as many as I could fit down the line here. These are all majors you can study as an, this information as an undergraduate, you can study it in graduate school, and you can be in on this. Why would you want to be in on it, by the way, neuromorphic computing? See, I have a piece of paper somewhere, I wonder where I put it. Yeah, probably lost it. But what it says is that the commercial money in this last year was somewhere around, I think it was 16 million, or 160 million. And next year, it's going to be about 4 times that, or 5 times that. By 2024, I found it. Okay, here's the numbers I saw online just today. 2016, $6.6 million in this industry. By 2022, $272 million in this industry. By 2024, we're talking $6.4 billion industry. That's why it's got a good future. Okay, so you want some fun reads, just to get a little background on this. I have a few books here I put together and a few websites. Oliver Sacks is always a good read. These are all very easy reads. If you're interested at all in autism, you can't go another day without reading Temple Grandin unless you already have. The Telltale Brain is a wonderful read. It talks about really how art is. What is art? Lots of topics like that. The Simulator is near. There's Kurzweil's book. It's a fun read. I haven't read Computational Brain, but I've been told it's pretty good. Okay, I already recommended the book of Genesis. Just download it, and there you are. About vocational raising. Oh, then here it is from Yale. Yale University has something much newer than Genesis, and it probably needs a little bit more computing power, but I'm sure we have it now on your home laptop. You can just download Neuron from Yale with all the documentation and go to town entertaining yourself, tinkering with this technology. OpenCV, how many people have used OpenCV? Anybody? Yeah, it's free, and it captures a lot of the neuromorphic strategies and the symbolist strategies and also the connectivist strategies for computer vision. It's a pretty darn good computer vision package. How about vocational read? Something a little bit tougher. MIT Deep Learning, can start there. Statistics. I'm going to move over to the right here right away. The probability people. Bayesian thought. Judea Pearl is the principal person that really put this thing into the industry. It's a good read. It's a tough read. It's very mathematical. Just a sideline on Judea Pearl. Does anybody know why his son became famous? It's kind of gruesome. Do you remember about 10 or 15 years ago that there was a U.S. correspondent from one of the news agencies that got beheaded? It was him, his son. He was like the first beheaded guy. Just thought you might not want to know. Any questions? Did I bore you to death? Okay, well, thank you for your time.